Hello everyone, my name is Wang Daowei. Today I'll be discussing a paper titled Attacking Deep Reinforcement Learning with Decoupled Adversarial Policy. Deep reinforcement learning is an AI methodology that combines reinforcement learning with deep neural networks, allowing agents to learn strategies by interacting with the environment to maximize rewards. This has led to applications in robotics, gaming, finance, and healthcare. Despite its potential, deep reinforcement learning faces challenges like symbol efficiency, exploration strategies, and safety concerns. Adversarial attacks use more carefully designed perturbations to mislead machine learning models, causing them to make incorrect predictions. While extensively studied in computer vision, adversarial attacks are relatively new in deep reinforcement learning. These attacks can significantly alter deep reinforcement learning actions with minor disturbances, categorized into white box and black box attacks. As deep reinforcement learning is increasingly used in real-world applications, like autonomous driving and financial trading, ensuring its security and robustness is crucial. Current adversarial attacks methods are limited in deep reinforcement learning environments. We need new methods to improve the speed and success rate of attacks, inform defense measures, reduce the number of disturbance injections, and optimize their timing. This lowers the computational cost and exposure risks while maintaining attack effectiveness. The key challenge is determining when to inject adversarial perturbations. Traditional methods inject at each time step, which is impractical and noticeable. Effective attacks require understanding the relationship between states and action and the cumulative effects of disturbances over time. Balancing the intensive and stealth of disturbances is essential to mislead the deep reinforcement learning model without detection. Then Li Qihui will continue the methodology part.
Hello, sir. My name is Li Qihui. Now we'll move on to methodology. Take a look at this architecture. The architecture begins by receiving inputs frames from a Pyongyang, denoted as ST. These frames are first processed by a CNN, which encodes them into one-dimensional figures. Alongside this, we compute pi ST, which represents the probability of each possible action given the current state ST. The output is then processed through a fully connected network, further encoding it into one-dimensional figures. The outputs from the CNN and the fully connected network are concatenated to form a sequence. This sequence is then fed into an LSTM layer designed to capture sequential figures, integrating temporal information over time. The architecture splits into two separate branches at the end, both implemented as fully connected networks. The first branch is the rule policy, which determines the actions to guide the victim agent up or down. The second branch is the switch policy, which decides whether to initiate an attack. The trigger for this system, highlighted in blue in the diagram, is activated when a switch policy outputs an inject signal, and the injection time remains below a predefined constant threshold. If these conditions are met, the system introduces a perturbation matrix, retrieved from a database into the state. This perturbation is designed to effectively manipulate the game within a given time constraint, aiming to achieve a successful attack policy. The attack launching stage is like this. We add a perturbation to the original input, and finally we get a new input like this. Consider that if inject times have run out, what happens? Inject time less than threshold is always false. So this attack will not launch, and the previous calculation will waste the computing resource. Therefore, we need to clip away all trajectories after the inject time reaches this threshold. For example, we have a trajectory T like this, where S is state, B is inject or wait action, A is action. Assuming at S1 trigger inject action and reach the maximum inject time, then the following state 2, state 3 until the end, we don't put them into training. Now we need to reconstruct our reward function. The T in the previous example, the T means from S0 to S1, and the T star is from S2. So this coefficient is always equal to gamma square. So that's how we calculate our reward. The clip trajectories can have great differences in layer length. Note that the shorter trajectory may indicate the case where the attacker successfully attacks the victim with few steps, which is essential to learn the optimal DAP. However, this precious data may be overwhelmed in the huge data from a longer trajectory. We need to find the maximum length of trajectory. So like we have 2 sequence, the first sequence has the sequence length 4, and the second has the length sequence 2. So the L max is 4, and for each trajectory repeat this time. So this for the second trajectory, the 4 minus over 2 ground and minus 1 equal to 1. So we will repeat 1 time, and the totally is 2 times. That's the end of my presentation. Thank you for your listening.
Hello everyone, my name is Kang Xin. Next, I will introduce two methods used during the training. The first method is decoupled proximal policy optimization. Why do we need to use DPPO? First, we need to know there are two policies, switch policy and lure policy, to control attack actions. At the time state T, switch policy take action BT and lure policy take action AT. The switch policy is used to decide whether to take an attack action. The inject means attack and wait means do not attack. The lure policy determines what kind of perturbations to inject into the victim agent. So the proximal policy optimization is a popular policy optimization method. However, for the DAP optimization problem, the PPO method cannot fully consider the relationship between switch policy and lure policy. So the equation 1 shows the objective function of the PPO method. The rho is the ratio of the new policy and the old policy, and use clipping method to find low clip. So if we use a PPO method, actually we are optimizing two policies independently. This will lead to a problem. When switch policy take action wait, which means no attack, but lure policy cannot realize that it doesn't need to inject perturbations. So the lure policy will explore AT, but this is meaningless and waste computational resources. So we need to use DPPO methods. And the DPPO method is based on the PPO and use the same objective function as PPO, which is equation 1. The key of DPPO is to connect lure policy and switch policy. So in equation 5, we can see the raw value of lure policy only be calculated when switch policy take action inject. This prevents the lure policy from performing meaningless exploration. And the second method is querying universal perturbation in real time. It is very time-consuming to find the best attack action by gradient descent in real-time attack. But if we can find some universal perturbation during training, then in real-time attack, the model only need to query and use the universal perturbations in the database. So to achieve this, we need to first define A times A minus 1 categories. The A is the number of actions in the action space. Then we need to label each category with action pair A and B. A is the victim agent's original action with respect to state S, and B is the wrong action we want to victim agent take with respect to state S. We can find the universal perturbations PAB for each category during the training process, and store this universal perturbation in the database. Therefore, the model can query and use the universal perturbation in the database. This allows model to perform attack in a short time. This is all my part. Next, I will pass to Kezenan to introduce the following content.
Morning, Professor. My name is Kezenan. I'm responsible for the results and the conclusion. And first, let's move on to the experimental setup. And in the experiments, the authors evaluate the effectiveness of the attack methods in various Atari games, such as Pawn, Breakout, Pac-Man, and Enduro, using DQN and PPO algorithms to train the victim agents. DQN outputs the Q-value estimates, while PPO outputs action probability distributions. Policy network includes CNN and a fully connected network and an LSTN, which used to capture state and policy features, ultimately outputting switching and inducement policy. And the authors employs and iterative methods to generate universal perturbations, ensuring a 100% success rate for adversarial attacks. The number of perturbations vary per type, such as 30 for pawn and 72 for mismatchment. When training the decoupled adversarial policies, we set the authors set a discount factor of 0.997, used GAE to compute rewards, employed the Ascent optimizer with a learning rate of 0.0007, and trained for 5,000 episodes. Experiments were conducted on high-performance CPUs and GPUs, utilizing the 24 redundancies to ensure the reliability of the results. And let's talk about experimental results. In the experiments, the authors compare the DAP attack with the baseline attack in games like pawn, breakout, mismatchment, and endurance, using DQN and PPO trained victim agents. The baseline attack lacks adversarial strategies with action limited to inducement and waiting. Results show that the DAP attack injecting perturbations once per cycle effectively reduce accumulated rewards in pawn and breakout, demonstrating the near optimal performance. In mismatchment and in Juno, the DAP attack also outperforms the baseline despite requiring the more injections. The authors use identical training algorithms and hyperparameters to ensure a fair comparisons. The charts highlight the DAP attack's superior performance, particularly in strict scenarios, underscoring the potential of decoupled adversarial policy in deep reinforced learning. And the T-start value represents the time step at which the attacker exhausts all injecting opportunities. The result shows that the T-start values for the DAP attack are higher, indicating that it can more effectively utilize injection opportunities, extends disruption time, and enhance attack efficiency and effectiveness. And they also compare the DAP attack with the ST attack in terms of the perturbation injection timing. In the game of pawn, ST attacks injects perturbations at multiple steps, like A, B, and D, whereas the DAP attack only injects at a critical step C. This makes the DAP attack more precise, avoiding meaningless attacks and delivering the stronger counter-attacks at crucial moments. They also show the comparison between the DAP attack and the antagonist attack, which varying numbers of perturbation injection steps. In the games of pawn and breakout, the DAP attack significantly reduced the victim's accumulated reward with just 2 injection steps, bringing the reward down to a -21 and 0, respectively. In contrast, the lowest rewards for the antagonist attack are 2 and 173. This demonstrates the DAP attack outperforms the antagonist attack in optimizing injection timing and strategies. And let's talk about the ablation test and the time complexity analysis. The ablation test analysis the impact of different components of DAP, like trajectory clipping and padding in data pruning, and DPPO in optimization. The results indicate that combining data pruning and DPPO enhance the stability and effectiveness of the attack strategy. The time complexity analysis shows that the DAP attack inference consists of 3 stages: plus policy deduction, universal perturbation querying, and attack launching. Each stage operates at a millisecond level, indicating that the DAP attack is efficient and suitable for real-time scenarios. And next, let's move on to the conclusion part. Experimental results shows that the DAP attack requires far less perturbation injection times in attacking the RL system, and thus possess higher secrecy. Ablation study shows that both components of data pruning and DPPO in DAP attacks are essential to launching a successful attack. Time complexity analysis indicates that the proposed DAP can be applied in real-time test scenarios. Via setting up the action space of the Lua policy, the DAP attack can be applied in tasks with the either discrete or continuous action space. In the future, the authors intend to extend the DAP attack to tasks with continuous action space and competitive multi-agent systems. And that's all for our presentation. Thank you.